Here we are, chapter 14. My gosh, we're going all the way to chapter 14 now. Chemical kinetics. What is that? It's the area of chemistry concerned with how fast reactions occur. So kinetic, movement, speed. You think of how fast cars go. This is how fast reactions go. So we'll be talking about reaction rates. And a reaction rate is equal to how a reactant concentration changes over the time change, and you have to multiply that by 1 over the coefficient for that reactant. And if we have a reactant, we put a negative in front because reaction rates should be positive. Reactant concentrations are decreasing while time is increasing. So we have a decrease over an increase. The ratio would be negative. A negative times a negative is positive. For the products, we don't stick a little negative in there. So the reaction rate is also 1 over the reaction coefficient times the change in the product concentration over the change in time. Because products are increasing over time, and time is increasing over time. And if something's increasing and you're dividing it by something that's increasing, you will get a positive number right here. Little note here, those brackets, should have seen those before, but in case you've forgotten or we haven't seen them, these brackets just mean concentration. So these rates, how do we actually measure these things? What does it mean, a reaction rate? Well, you take some data, you run an experiment. So here's some data for an experiment. It's made up data. There's no actual axis here with numbers, so they're just this is what it would look like theoretically. So here's our reaction. Hydrogen and iodine reacts to make hydrogen iodide, and this is balanced. So notice the blue here, those would be our products increasing over time and our reactants decreasing over time. So this one would represent their hydrogen and the iodine. Up here would be the hydrogen iodide. And the way you actually measure a rate, at any point in time, if you have this data, concentration versus time, the rate is the change in concentration over the change in time, and that is the slope of the line tangent to this curve above at any specific point in time. And then you have to divide that by the coefficient of the chemical in the reaction. So right here, notice this little triangle here, they're taking a tangent line to the red curve at this point right here. And so at that point, the Y value, concentration of H2, is changing by this much, and the X value is changing by this much. So we would do the Y value over the X value. Y over X is slope. So this would be our slope of the tangent line, the line tangent to a curve. It's where it touches the curve at just only one point on the curve. Right over here, we're looking at the tangent line. Looks like they're looking at it right about here. It seems a little bit off there, but this would be the reaction rate at a different point in time. So this one would be at this time right here, and over here, this rate that is being measured would be at this time right here. So the rate is, we put a negative in front of reactants, and notice the stoichiometry here. There's a 1, and a 2. So the change in hydrogen over the change in time times -1. Change in iodine over the change in time times -1. And then hydrogen iodide over the change in time times 1/2. And there's no negative because notice the slope is positive. These slopes are negative, and the negative slope times a -1 will give us a positive rate. And these are all equal to each other. The only difference is there's a 2 in front of the HI. So the rate at which this is produced is twice as large as the rate at which this is produced. Therefore, we need to divide this by 1/2 because the hydrogen iodide is being produced twice as fast as the iodine. So that's why we have 1/2 of the change in HI over the change in time. You always divide by the coefficient. Basically, you're taking the rate as though the coefficient were 1. So if the coefficient's not 1, it's based on a 1 molar change. So if the coefficient's not 1, you have to divide by the coefficient to get the rate as though this reaction were a 1 molar per 1 molar change. All right, so let's do a problem. You are given how fast molecular oxygen is reacting. So here's our reaction right here. And you're told how fast the oxygen is reacting. So our rate of reaction would be, this is the change in oxygen over the change in time. It's actually the negative of the change in oxygen over the change in time because this is a positive number. So we want to find what would the rate of N2O5 be. So this is just stoichiometry. We're just going to convert from oxygen to N2O5 for part A. You can try to set this up and pause, but I'm going to show you the thing right now. Pause if you want to. So the rate of change of N2O5 should be a positive value because N2O5 is a product. We know the O2 is reacting at 0.024 moles per liter second. Remember, molar is moles per liter. And then for every 1 mole of O2, we make 2 moles of N2O5. Right there is our stoichiometry conversion. So we are making N2O5 at 0.048 moles N2O5 per liter second. And it was what is the rate of change of this stuff. And that is a positive amount because the dinitrogen pentoxide is increasing. So we should have a positive rate of change. Now if you want to try the NO2 on your own, pause because I'm showing you the answer right now. Okay, NO2. Now NO2 is a reactant, so the rate of change of NO2 should be negative because NO2 is decreasing. So we have a negative in front of here. The oxygen, we were told how quickly oxygen was changing. There's 1 oxygen for every 4 NO2s. So the NO2 is decreasing at this number right here, and the rate of change is negative. Now note, if we were to ask what is the rate of reaction based on the NO2, we would take this number and divide it by 4. Remember, you say you take the rate of change, the change in concentration over the change in time. That's what this is right here. For reactants, the rate would be this number divided by the coefficient, and for reactants, we would multiply this by -1, giving us a positive rate of reaction. Moving on, rate laws. These are fun. They're actually really fun once you start doing them. I mean, I love doing rate laws. Okay, rate law is an equation that defines how fast a reaction occurs. It's a mathematical construct. Looks just like this. A, B, and C are your reactants. This is all written for you in a moment. Those are your reactants. X, Y, and Z, you determine those experimentally, and this K here is called the specific rate constant. And that specific rate constant is also determined experimentally. So here's all the information that I just was telling you about. Oh, A, B, and C, they could also be a catalyst. We're going to learn about that later. The exponents we get experimentally, and they have a term. It's called the order of reaction with respect to a reactant. So X is the order with respect to A, Y is with respect to B, Z is with respect to C. And the order of reaction has a physical meaning, which you are not ready to learn. We will learn about that about 3 more sections. And K, right here, is called the specific rate constant. It's also found experimentally. There's also something called the overall order of reaction, and to find that, you just add the exponents for the orders of each of the individual species. And we find that the overall order of a reaction is usually not more than 3. You don't need to memorize that, but you'll find out later why that is. It would be called a termolecular collision if you had 3 things reacting. And if you have 3 particles colliding, you'd have an order of 3, which gives you a little hint about what the order is. We'll learn about something called mechanisms later. All right, so easy problem. We have this reaction. You can pause this and answer it yourself. I'm going to put up the solution in just a moment. Here's our rate law. What's the order with respect to oxygen and nitrogen, and what's the overall order? Well, you just look at the exponents. Go ahead and pause if you want to, but here we go. Pretty darn straightforward, right? It's just the exponent. Very straightforward on this one. Okay, pause if you need to, and here's the answer. Boy, that was easy. At least I hope it was easy. Now comes the fun part. Little confusing at first, but just stick with it. It's not hard. This is fun. This stuff is actually really fun. Okay, so somebody runs an experiment. You run 3 different experiments. In one experiment, we know the initial concentrations of our reactants, and we measure the rate. Remember this little graph here? This is how we get our rates. We run an experiment like this, and we get our rates. Okay, so somebody ran an experiment at some point and got these data, and we're going to use those data now for our work here. You've never done this, and what we want to do is find the order with respect to each reactant and the overall order of the reaction, and also write down the rate law. I'm just going to remind you, the rate law is this thing right here. So when I ask you to write a rate law, you need to write this down. A lot of students solve the whole problem, they forget to write the actual rate law. Okay, so here's our data. We want to find the rate law, and here's how you go about doing the problem. You find 2 experiments where all but one reactant concentration are constant, and you substitute the values for the experiment into the rate law, dividing the larger by the smaller. Don't worry, I'll explain this as we go along. But let's just look at these 2 things. We're going to use this and go through the solution. 2 experiments, all but one reactant concentration are constant. Let's do that. Let's see, 2 experiments where all but one are constant. Look at this, 1 and 2. F2, the fluorine concentration is constant, and the chlorine dioxide is changing. So I could use those 2. Now it tells me substitute the values for the experiment into the rate law. So I have a rate right here. I will have rate equals K, 0.1 to the X, 0.04 to the Y. And I'm going to divide the larger initial rate experiment by the smaller initial rate experiment. Let's see, experiment 2, the initial rate's larger than experiment 1. So I'll do experiment 2 over experiment 1. If you want to try to plug it in, you can, or you could just look, and here you go. Actually, hold on a second, let's do it this way. So we're doing experiment 2 over experiment 1. Oops, I don't want you to see the next part yet. And all I did was plug in those values. So if you look back up here, I plugged the fluorine and chlorine dioxide concentrations in. These ones on the top, these on the bottom. I just plugged right in from these experiments 2 and experiment 1 using the rate law. And now you should notice, do you see that the K's cancel out? Choop. And the 0.1 to the X cancels out. Oh, that's so easy. And now this simplifies into just the number 4 to the Y. They're both raised to the Y, so I can simplify that. 4 to the Y. And if you divide this, you get 4. So let's look at that now. We get 4 to the Y equals 4, therefore Y equals 1. Look at that, we just found out what Y is. Now, let's see, solve the resulting equation for one of the exponents. We just did that. Repeat the process for all the other reactants. Don't worry about step 5 yet. Okay, so now we have to do this for chlorine dioxide. I'm about to tell you how to do it. If you want to pause and just do this next one yourself, you can. But here we go. Notice experiments 3 and 1. Chlorine dioxide stays constant. I want to use the experiment with the larger initial rate in the numerator. You don't have to. It just makes the solution easier. So I'm going to do experiment 3 over experiment 1. And I have the rate will equal K F2 to the X, ClO2 to the Y, and I divide it by experiment 1. And this is what it's going to look like. Okay. And you see what you can cancel. The K's cancel. That one doesn't cancel. None our 0.010 to the Y's cancel. That simplifies beautifully. And this simplifies into 2 to the X. Hopefully you see that. This is 2 to the X. This is just 2. When you have 2 to the X equals 2, do you know what X equals? X is 1. Okay. So now I know the order with respect to Y and the order with respect to X. Just 1. The overall order, you just add these. Overall is 2. And the rate law, you just plug in your values. So this is our answer right here. Rate is K, F2 to the 1. You don't have to put the 1 up there, it's implied. ClO2 to the 1. First order with respect to F2 and ClO2. Second order overall because we add the exponents. Next time we're going to learn about how to solve for K. But right now, real quick, number 5, step 5, you'll want to read through this. Sometimes it's a little more complicated. We will do a problem like this a little later on. Okay, next problem. If you feel like you know how to do this, go ahead and do it. All right, this time we're going to get the rate law, and we're going to calculate the specific rate constant. So, rate law, look for 2 experiments. Again, pause if you want to do this on your own. Look for 2 experiments where something is constant. I see experiments 1 and 2. The H2 is constant. So I plug into the rate law. I'm going to look over here. Let's see. This one is a bigger rate, so I will use experiment 2 in the numerator, experiment 1 in the denominator. And I get this. Okay, I can simplify my K's. Those cancel. This cancels. And if I look at this, this is 2 to the x, simplifies 2 to the x, and this one becomes 4. 5, these cancel. I don't know if you realize that, those cancel. 5 over 1.25 equals 4. 2 to the x is 4, x is 2. Okay, now let's look for another set of experiments. Oh, look at this, 2 and 3. The NO is constant, the H2 is changing. I look to see which rate is larger. Experiment 3, the rate is larger. I'll do experiment 3 over experiment 2. Again, that's not necessary. It just makes the solution easier. If we had done this one the other way, I would have gotten 1/2 to the x equals 1/4. Now, you might find that that's really easy to do, but a lot of students don't leave these in fractions, and they would have 0.5 to the x equals 0.25, and many students don't know what to do with that. So, when in doubt, just put the bigger rate on top. So you start with the experiment with the larger rate on the numerator. Okay, we're doing experiments 3 and 2 right now. Experiment 3 has a larger rate, so we'll do 3 on top, 2 on the bottom. Again, pause. This is what we get. Let's see what simplifies. The K's cancel out. These cancel out. The 10 to the 3 cancels. The 10 to the minus 5 cancels. I have 4 over 2 is 2 to the y equals 2. Y is 1. I've got my rate. Look at that. Now, you might have gotten to this point and then there was another part to the question which said, what's the rate law? We just got the rate law. What is the specific rate constant with units? To get a rate constant, once you find your rate law, it's so straightforward. You just plug the information from any of the experiments. You can pick 1, 2, or 3. I usually use experiment 1 just because it's the first one. But you plug the initial rate as your rate. K is unknown. You plug in the concentration of NO and you square it. You plug in the concentration of H2 and you square it. So we plug these into the equation. And pause if you want to, but here we go. You got to make sure you include your units. So I've just plugged everything into the equation. Now I'm going to isolate K. Students get very confused about these units here, so let me show you what I did. Ignore this piece for now. Okay, so here's my 1.25 times 10 to the minus 5. This part squared is 25 times 10 to the minus 6. Bring it over to the other side. This piece right here comes down in the denominator of the other side. On the left side I had molar per second. And now on this right side I've got molar squared and molar. So I have to move those over to the other side. They will be in the denominator, molar squared and molar. So these you can calculate out and you get back that, oh shoot, there we go. Let's put that back. Oops. Okay. This all comes out to 250, and your units, when you simplify them, come out to 1 over molar squared seconds, because one of the molars cancels out. So you have 1 over molar squared seconds. Okay. Just some quick exponential practice problems. Pause this. I'm showing you the solutions right now. So pause, 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 pause. Don't forget to recall this piece little here. This little piece here. Here's your answers. All right, last problem. Challenge problem. This is going to be like that, number 5. Okay, so notice we have, well, we want to find the rate law and the rate constant for this reaction. This time we have 3 reactants, 3 concentrations. So again, we need all the concentrations but one to be the same in order to solve these. So if I look here, again, start solving it on your own if you want. You will get stuck. You can find the exponent for the oxygen and the NO, and you get stuck on the NO2. And I'll go over how to do that. That's the step 5 piece. Okay, so again, you can pause and just do this on your own, but here we go. Experiment 2/1. There we go. We can do some simplifications here. Choop, choop. You get 2 to the x is 2. Very easy. X is 1. Then we see experiments 1 and 4. NO stays the same. Nope, not 1 and 4. That won't work. Oh, there is one. I keep losing it. I have it written over here. It is 1 and 4. Oh, right. These 2 stay the same in 1 and 4, and this one changes. So 1 and 4, we can simplify this. The k's cancel, the 0.1's cancel, the 0.1's cancel. We're left with 2 to the z equals 1. And that's one of those tricky ones. What raised to the 2 raised to what power equals 1? The power has to be 0. Okay, now we're stuck. We can't find something for this middle part where this and the NO are both constant. So what we need to do is just pick 2 experiments, any 2 where the NO2 is not constant. It won't work if you have NO2 being constant, and I apologize about that piece being backwards. Okay, so any 2. I decided to pick experiments 3 and 1. You just plug the values in and plug in the value of z and the value of x. Don't leave these as unknown variables because we know what they are now. So here's what you do. You just plug it in. I happen to do 3 and 1. You could pick anything. You'll get the same result. K's cancel. These actually cancel because they're raised to the 0 power. This number is just 2. I'll have 2 times 3 to the y equals 6. This divided this is 6. I divide both sides by 2, sorry. I divide both sides of this equation by 2, and I get 3 to the y on the left. 6 divided by 2 is 3. So 3 to the y is 3, y equals 1. Oh, we are golden. There's your rate. And if I have something raised to the 0 power, I do not need to include it. So I would have had oxygen raised to the 0, but you don't even need to write that down. All right, now solving for K. You pick any experiment. I just picked experiment 1. Plug these data right here into your rate law. And there you go. Let's isolate K. We've isolated K. You have to divide both sides by 0.1 molar. Notice I separate the units out from the numbers, and then the numbers become 2.1, and then the units, we have to look, this molar and this molar cancel, so I'm left with 1 over second molar, or 1 over molar second. And that's it. So we're done. You've got some practice on your own. These are in the book, and that's it. Enjoy.